We're going to continue to look at this very, very specific example of a one-dimensional head-on collision. It is elastic, and the target ball, number 2, is initially at rest. So we derived this equation here. So the final velocity of the incoming ball, right, is given by this equation, and it was a little bit of algebra, and we're not going to go through the algebra to calculate the velocity of the target ball, the one that's at rest, when it gets struck. But we do want to notice a couple of things. One is both of these velocities only depend on the velocity of ball 1, the incoming ball, because that's where all the momentum is initially. So anything that's happening to these balls after the collision had to be a result of that initial momentum. Well, let's look at the possibilities. The first possibility we have is that the incoming ball is less massive than the target ball number 2 that's at rest. And let's exaggerate it for our example. Let's make the incoming ball a ping pong ball, and we'll make the target ball bowling ball. And for our example, let's go to outer space and say they're floating in outer space, so no air resistance, no friction. The ping pong ball comes streaming in, hits the bowling ball, and as you can imagine, it will bounce off the bowling ball according to this equation. Since M1 is less than M2, that bracketed term gives us a negative, which corresponds to it bouncing backwards. Notice the green M2 mass has no choice but to go forward, even if that ping pong ball barely put a speck of a force on it during the collision to the right. Doesn't matter, F equals ma, that force to the right means that the target ball, that bowling ball, has to go to the right. Well, let's reverse the situation. Now, let's make M1, the incoming ball, the bowling ball. And M2 is now going to be the ping pong ball. So just as you would, I think, imagine intuitively, the bowling ball is going to steamroll the ping pong ball and continue going to the right, and the ping pong ball, of course, continues to the right as well. It has no choice because the force on it is in the forward direction, and that forward direction still comes about because of that bracketed term. The forward direction for the M1 ball comes about because of our bracketed term, where M1 is now much bigger than M2. But if it's bigger at all, it will go forward. Now, one of the most interesting results is when M1 equals M2. So what do we think is going to happen when M1 equals M2? Well, if we let our equation guide our answer, M1 minus M2, if the masses are equal, means we have no V1 final. Notice now, if M1 equals M2, we have a 2M on the bottom, a 2M on the top. You can drop the subscripts, they're all the same mass. 2 divided by 2 is 1, so the velocity of the target ball now has the velocity that the incoming ball had initially. So it gets all of the momentum. So that's exactly what happens. So this is the not necessarily intuitive result that if we have a perfectly elastic head-on collision, all of the momentum of the incoming ball is transferred to the target ball, and the incoming ball is at rest. And again, our bracketed term shows that it's at rest. And if you have ever seen, many students have from middle school, or kind of that neat little Newton's Cradle, clink, 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 click, 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 where if we drop equal mass objects, so they all have the same m, and let it come slamming in so that when it gets to the bottom here, it is a one-dimensional collision, head-on, that you have this instantaneous hit-stop, right? So we have it hit, stop, and the next one goes, but it's like a domino effect, hit, stop, hit, stop, hit, stop, and finally the ball on the end has nothing to hit, so it goes up, and in the perfect conservation world, it would go up with the same V that this one had when it hit at the bottom. Well, And this type of conceptual analysis, when they have equal masses, is often in test banks on this unit. So I do want to make sure you have practiced thinking about what will happen to predict the outcome. So your homework is to look at these 4 examples and predict the outcome of the click when we pull 2 to the side and let it hit 3 when we pull 1 apiece, 2 and 1, or 3 and 1. And we will go over these examples in class together.